This is a video for AQA Mechanics, Work, Energy and Power, section 2.2. We're looking at the elastic potential energy stored in a string or spring. We've already met the idea of energy stored in the form of gravitational potential energy when something is held above the ground. But we can also have energy stored in strings and springs that are compressed or stretched, and that energy is then released when the spring is released. For example, an elastic band, if it's pulled and then flicked across the room, the energy stored in the elastic band becomes kinetic energy. So we refer to this energy stored as being elastic potential energy. The energy comes from the fact that when we stretch a spring or a string, we have to actually do some work, and that work we know is the integral of f dx. It's a variable force because the force gets greater the longer the spring or the string gets, and the value of f is given by Hooke's law, and Hooke's law tells us that f is equal to kx. And therefore we can say that the work done in stretching spring from 0 to a distance x is the integral of kx, and that gives us a half kx squared. Now it turns out that k is equal to lambda over 2l, where lambda is the constant for a particular spring, and L is the natural length of the spring. So we have that the work done, or the stored energy, is equal to lambda x squared over 2L. So in systems we can use this in the same way as we use gravitational potential energy and include it in energy calculations. Consider this simple example then, where we have a string of natural length 1.5, so this means that the value of L is equal to 1.5 meters. Modulus of elasticity, that's lambda, is equal to 50 newtons, and we have it stretched to a length of 2 meters. Therefore the extra extension x must be equal to 0.5 meters. So we know that the stored energy, the elastic potential energy, is equal to lambda x squared over 2L. So that will be equal to 50 multiplied by 0.5 squared divided by 2 times the natural length 1.5. And that turns out to be 4.17 to 3 significant figures, and because its energy units are joules, so 4.17 joules. In a situation where there are no what we call non-conservative forces doing any work, then we can say that the total energy is conserved, so that we have that the final energy, this includes kinetic energy, potential energy in the form gravitational and elastic, must be equal to the initial energy, kinetic, gravitational and elastic. If there are forces doing work, then we can still use this, but we need to include these energies in any equations. In this example then, we have a light spring. Light, remember, is just a word which is used to say that we can take the mass of the spring as being negligible. We've got a natural length of 40 centimeters, so there's L is equal to 0.4 meters. Modulus of elasticity, 180 newtons, lambda is 180. Fixed to O, and then it's stretched away from O to a distance of 55 centimeters. That gives us an extension x of 0.15 meters. can see on the diagram then that we're going to have elastic energy stored in this spring because we've stretched it, and there's now some force here acting towards O. We've stretched it out. There are two other forces. There's a normal reaction and the weight mg, but these are both perpendicular to the direction of F. They're vertical forces, and so they're not going to do any work in the direction of F. So we can say therefore that the elastic potential energy is equal to lambda x squared over 2L, and putting in our values we've got for lambda 180, x 0.15, so we're squaring that, and divided by 2 multiplied by 0.4, and if you calculate that, it turns out to be 5.06 joules. So therefore the work done in stretching that must be equal to the elastic potential energy, which is 5.06 joules. So the work done is equal to 5.06 joules. In this final example then, we have a mass of 5 kilograms, which is attached to one end of an elastic string of natural length 4 meters. So L is equal to 4 meters, and modulus of elasticity lambda equal to 150 newtons. And it says the other end of this string is attached to a fixed point O, and it's then released from rest. And we want to find out how far the object falls in the subsequent motion. Let's put that onto a diagram first of all. So you can see that at the top there we've got the object, and then towards the bottom we've got it at a height h. Now compared to the top, we've gained potential energy. Coming down here, the kinetic energy at the top will be 0, and at the bottom, because the string has stretched and brought the object to a stationary position. So this is like a bungee jump. So the kinetic energy will be 0 at both points, but then we've got at the top a potential energy of mgh compared to the bottom. And also then at the bottom we'll have gained some elastic potential energy. So if we put in the values for that, we can see that the gravitational potential energy mgh, 5 multiplied by 9.8 multiplied by h. And at the bottom we've got then elastic potential energy, which is equal to lambda, the extension, so that's h minus 4 squared, divided by 8. 4 was the natural length of the string, and 2L giving us a value of 8. So the conservation of energy says that the gravitational potential energy at the top then will be equal to the elastic potential energy at the bottom. So we can put that in. This rearranges to give us a quadratic in h, which is 150h squared minus 1592h plus 2400. That, of course, we can solve to give h is equal to 1.82 or 8.79. Now we can discard one of those, because if h is 1.82, then it's actually above the point of the string becoming stretched, so it would give us an extension which was negative, and that wouldn't be possible. So we can disregard the 1.82, giving us h is being 8.79 meters below the point. So the lowest point reached is 8.79 meters below our starting point. Well, that's the end of this video on elastic potential energy. In the next video we'll be considering the idea of power.